So finally, the last insight, and maybe a synthesis of the others, is that you are also part of the universe. And obviously you're part of the universe. What could this possibly tell us, that we're part of the universe? But actually, because you're part of the universe, this is very related to the fact that every observation that you make is observer dependent, because you have to make it. You have to perceive the universe through fields or particles that reach you, and therefore everything is based on your point of view. There's no absolute point of view. The only physics you could possibly have is a physics that's consistent to your point of view. And as I said, every surface could be thought of as a hologram or as an abstraction that gives you those particles that appear to make sense to you. The other is that you're made of particles, and you can only sense the universe with particles. That has a sort of mechanistic explanation of why you cannot observe everything perfectly, because if you try to observe a photon with another photon, you can only scatter one photon or electron against another and observe the result indirectly. You cannot observe the photon itself. If you want to look at that kind of even more deeply, every particle has a few degrees of freedom. It has like 2 in the case of a free light speed particle, 3 in the case of some others. And you are a gigantic vector of degrees of freedom. You have many more. But because of conservation of information, you cannot duplicate the degrees of freedom of the particle in question and kind of have a macroscopic you cannot take one particle and make 1 billion clones with the exact same quantum degrees of freedom, quantum numbers, and just look at them macroscopically. So because that would violate conservation of information, the best you can do is kind of mingle, or the proper word is called entanglement. The best thing you can do is you can entangle your degrees of freedom, or of your instrument, effectively your degrees of freedom with those of the particle, and that means that at most you can obtain some degrees of freedom, or a combination of degrees of freedom. You can ask a question: tell me something about the relationship, tell me something about the momentum of the particle, tell me something about its position, tell me about something about the relationship of these two. But you cannot say, give me all of these facts together, because if you did, either you'd be destroying information, or you'd be destroying the particle, or you'd be destroying you. So because you cannot just duplicate information like you can in a normal computer. There's no ability to create copies. So this fact that you are also part of the universe means that any physics that you make has to be essentially from the only thing you can test is what you can test as a human in the universe. That has to be based on a point of view. It has to be observer dependent. It's not surprising in any way that your results that you come up with will be observer dependent, and it has to be limited, because because of conservation of information, you cannot extract full information out of anything. You can at best entangle yourself with the experiment. And so any theory that you have has to be a partial. It has to be phrased as, if I entangle myself partially with the universe, what would that feel like? And you can only get like a partial grasp of what is happening. You can, if you want, make like a complete. You can make a kind of philosophical idea that there is a complete information someplace, but it's inaccessible to you, because you are also made out of the same kinds of degrees of freedom as the rest of the universe. And because they don't duplicate, they just get rearranged and entangled with each other in kind of different combinations, the totality of the universe is just inaccessible to you, both because of distance and because of this microscopic phenomenon. And therefore any physical insight that you make has has to be colored, has to be seen through this very limited prism that you can only get a partial readout of what's happening. And the more philosophical way to think about that is that, we are big heavy beings with in the length scale of meters. The universe goes down to 10 to the minus whatever 15, some small number, and an equally large number in the other direction. And so why should we, since we're observing everything from our point of view, it's natural that it should be over time less and less intuitive. That if we use intuitions like particle or wave, or these intuitions will get increasingly less meaningful as we go deeper and deeper. And in my opinion, I think intuitions like superstring are already beyond any point of being helpful. So I think at some point we should acknowledge this and stop making a theory directly as if what we see is what exists. We should instead maybe making some other theory that says, well, if someone had programmed the universe as a simulation and there are some abstract degrees of freedom, what would they do? Hello? So if someone had programmed the universe in terms of abstract degrees of freedom, it effectively will come up with some kind of generalized quantum computing theory that explains the entire functioning of everything. And then the way you test that theory, the way you decide what's real or not, is whether the very, very partial or narrow perspective that we have on such a theory, whether it helps explain our experience. But you cannot directly test it. You can only say it's unhelpful to carry our intuition from our perspective too far and say, well, superstrings really exists, or multiple universes really exist, in the sense that, the mountain exists over there. I think that intuition is kind of already out of place, and instead we need to come up with a much more abstract and computational idea of how these degrees of freedom interact and kind of compute, do operations with each other. And then we have to say how space and time and particles and waves and big things like humans, how we come to emerge from that deeper theory. And I think that when people search for a grand unified theory, they should stop phrasing it in kind of intuitive terms and use intuitive pieces as ingredients. They should just use imagine that you were programming a simulation in the abstract, and what would it look like to an observer-dependent, what would the observer-dependent reality be if you were in such a simulation? And that's the only criterion. Now you can ask, is that real? And what does it mean to be real? What is the meaning of real in physics? So one approach that has been the dominant approach is, well, it's real if it's confirmed by experiment. So if we can actually see the thing, then it's real. Well, sure. So that works while the thing that we can observe is relatively close to our intuitive world, and therefore you can make a kind of intuitive observation. You can put things on inclined planes or drop them from towers and see how solid objects move. And that intuition is already gone in terms of quantum mechanics, and you end up with a very mathematical and intuitive thing. But I think at some point this intuition will fail us completely. So we have to say that what is real, a theory is real if it is robust and if it helps explain observations. So robust means you put out your theory, and then more facts happen, more facts get uncovered. You shouldn't have to change your theory all the time. So I I could give you a theory about the behavior of children by listing all the previous behaviors I've seen in children. It would be a good theory. You could explain facts. But then a child would do something new, and my theory would be useless. I'd have to revise it. And so that's an example of what not to do. That's the opposite of robustness. And as far as I can tell, superstring theory and some cosmological theories have had these sort of robustness problems where they appear to make a prediction and then they have to be revised in the light of evidence and again. So they get like partially falsified rather frequently. So I think this problem comes from having too much detail phrased in a kind of human perspective, that there are little strings or little universes and such, and that the physicists would have more success if they got rid of that detail and became more abstract and just expressed the relationships that they wanted to express. And of course the other part of real is that it helps to explain observations, but the observation have to be knowingly incomplete. So we know that we can only observe things from our point of view, and it's perfectly fine. It's not neither good nor bad philosophy to imagine that there are multiple worlds, or that there are imagining counterfactuals is fine. Having counterfactuals in your theory is fine. It is just not anything that you could confirm or deny. So your theory has to stand on the ability to explain our very particular human perspective on the universe, from our partial ability to digest information, our dependency to receive particles through essentially a large sphere containing the Earth for all practical purposes. That has to be, if you come up with a abstract theory based on abstract degrees of freedom that produces space-time explains why we experience the space-time that we do experience by looking around the Earth, then you have a good theory. And that theory would be real, because it would be robust and it would help explain observations. And it doesn't matter if it's abstract or if it's phrased in a human-centric form. It will be just as real either way. All right, thank you.